There we go. Okay, so here we go. Answers. Number one, just wanted two definitions of mass. So mass is either a measure of how much matter is in an object or a measure of an object's inertia. Good?
Yeah.
All right, number two, which has more inertia is a really stupid way of asking what has more mass. So the answer is A, elephant, B, whale, C, it is a tie. Good? Number three is also a dumb question. 2 kilograms, is it twice as much inertia as 1 kilogram?
Yes.
Is it twice as much mass? Yes. All right, number 4 is about the difference between mass and weight. All right, so remember you guys, mass is, man.
The markers are number 2.
Yeah, I got them back. The person who took them, who I am leaving nameless.
Well, they stole them?
They were playing a little joke.
You figured it out. Were you mad?
No, not really.
Wait, so where do they have that? They
In
just
the
have.
backpack.
Why would you
I thought they like.
I thought you like
But
lost
someone
them.
got like
Wait, what?
I did too until I knew that I had 2 of them at the end of third hour yesterday, and then I suddenly only had 1, and then I was like, pee. All right, so anyway, all right, so number 4 is about the difference between mass and weight. All right, so check it out, you guys. Mass is an intrinsic property of an object, okay? And it's determined by how much matter is in the object, okay? So this C clamp here is made up of 7 bajillion molecules, okay? And no matter what I do with it, no matter where I take it, it's always going to be 7 bajillion molecules. So whatever its mass is now, if I take it to the moon, or Jupiter, or the top of Mount Everest, or the bottom of the Grand Canyon, or to the asteroid belt, or whatever, it's always going to be 7 bajillion molecules worth of mass, and the mass doesn't change. Good? So, questions 4, A, B, and C. 4 says a box has a mass of 20 kilograms on Earth. If I take it to the moon, what's the mass? 20 kilograms. If I take it to the moon, or if I take it to outer space, what's the mass? 20 kilograms. The mass stays the same. All right? Now, questions C, D, and E ask about weight. Weight is not a property of an object. Weight is about an interaction between the object that you're discussing and usually the planet that the thing is on. Okay? On Earth, we have gravity because of science. We'll talk more about that later. But basically, the Earth has a large amount of mass, and that mass attracts things towards it. Okay? Jupiter is much larger than the Earth, and so it attracts stuff with even more gravitational force. The moon is smaller than the Earth, so it has gravity, but not as much as the Earth does. Okay? So when I hold this up in the air, it has mass, 20 kilograms, whatever. Gravity from the Earth attracts that 20 kilograms worth of mass downward with some force. Okay? But if I take it to the moon, that force is not as strong because the moon doesn't pull down with as much force. And if I take it to Jupiter, it's going to weigh more because Jupiter attracts stuff with more force. Okay? So weight is it's an interaction between 2 objects, and it's the force of gravity on the object. Okay? So when I ask you to find the weight, I'm asking you to find the force of gravity, because that's the definition of weight. Okay? So force of gravity is mass times whatever the acceleration of gravity is wherever you're at. Okay? So, for 4C, what's the weight of the box on the Earth? Well, I'm going to take 20 kilograms and multiply it by negative 9.8 meters a second squared, and you get negative 196 newtons. Why is it negative? Because gravity pulls stuff down, right? All right, now if I want to find the weight on the moon, I'm going to multiply the mass by the acceleration of gravity on the moon, which is about 1.6 negative. So you get about negative 32 newtons. Good? What about in outer space? Way in the middle of nowhere outer space where there's no gravity. The weight is 0. Because there's nothing for the thing to be attracted to. Good? Questions on mass or weight? Cool. All right. Number 5. What do we measure mass in? Kilograms. 6. Definition of force. A push or pull on an object. Number 7. Units of force is newtons. Number 8. Definition of weight. Force of gravity. Number 9. What units do we measure weight in? Well, it's a force, so we measure it in newtons. problems up through number 9? I ran through those super fast. Do I need to say more about any of them? No. Okay. Number 10, you just had to say mass or weight. 15 kilograms is mass. 15 pounds is weight. 15 newtons is weight. Good? Everybody happy? Okay, you good? Sheet up. We're good? Okay. Number 11, you were given the mass of the object, you had to find the weight. So just multiply by negative 9.8. So for A, it's negative 39.2 newtons. For B, it's negative 98 newtons. For C, it's negative 294 newtons. Good? Okay. Number 12, you had to go the other way. This time I gave you the weight of the student, or the weight of the object, and you had to find the mass. How do I know those are weights? Because they're in newtons. Okay? And we're describing the object. So, this is how, this is how we find weight. So to find mass, we're going to algebraify this guy and solve for m. So the mass is going to be Fg over Ag. So, to find the mass of my student, I'm going to take 600 newtons, because that's his weight, and I'm going to divide it by the acceleration of gravity on Earth. Divide it out, and you get negative 61.2 kilograms, and we are all done, yes? Oh. You can't have a negative mass because something can't be made of a negative number of molecules. So I made a mistake somewhere. Don't just change the answer to positive. That's cheating. What do you got, champion? Wait a minute. Why is the 600 newtons negative? Because gravity pulls stuff down. Now, negative divided by negative gives us a positive answer. Hooray! Cool? Any problems with whatever number that was? 12. All right, so 12A, that's the answer. B is what, 2.04 kilograms, I think? And C is 14.29 kilograms? What is it? 8. Okay, sorry. I lost my answer key somewhere, so I'm doing this from memory. All right. Everybody good? Okay. All right, 13 and 14. I'm guessing most people did okay with 13, but a lot of people, as I walked around, said, I didn't understand 15. And to understand 15, you have to understand 13 and 14. So I'm going to plow through 13 and 14 real fast, and that'll help us understand 15. Cool? All right, here we go. 13 and 14. In number 13, it says ball A has a mass of 4 kilograms. So here it is. Here's ball A, 4 kilograms. In number 14, oops. That took me more time to process than it should have. In number 14, we've got a larger ball that has a mass of 8 kilograms. Question A on both of them says make a drawing of the ball. Check. With all forces labeled if it's in free fall. So free fall means yes, but why? What were you going to say, Caroline? Oh, didn't you have a hand up?
No air.
No? It means no air resistance. It means the only force is gravity. Okay, so let's find our force of gravity. So the force of gravity is negative 9.8, right? No! The acceleration of gravity is negative 9.8. The force of gravity is 4 times negative 9.8, which is negative 39.2 newtons. Good? What, you good? What's up? You're very animated back there today. You're okay?
Yep.
Okay. Everybody's happy?
Yep.
All right. So over here, same idea. Force of gravity, 8 times negative 9.8, you get negative 78.4 newtons. All right. So that is part A. Does anybody have questions with part A? All right. Part B says, what's the net force? What's the net force? Well, isn't the only force gravity? So my net force is going to be negative 39.2 newtons. And over here, my net force is going to be negative 78.4 newtons. Good? All right. Part C, as in cat, says find their acceleration. And I'm guessing most of you just said, it's negative 9.8 and called it good. Yes? Awesome. Great. That means you understand free fall. And to make sure that you understand 15, let's take a minute, and it's a little bit silly, but let's calculate the acceleration. Okay? Acceleration, according to Newton's second law, is determined by the net force acting on an object and the mass that the object has. So, for this guy, my net force is negative 39.2 newtons, and the mass is 4 kilograms. And when I divide it, no big surprise, you get negative 9.8 meters per second squared. Yes? All right, now, this bowling ball is bigger. Common misconception, heavy stuff falls faster. Why would that be true? Well, it's heavier, so there's more pulling it down. Well, let's see. Let's find the acceleration. So acceleration is net force over mass. Uh-oh. I am nervous because our net force is totally way bigger. Right? This thing only had 39 newtons pulling it down. This one's got 78 newtons pulling it down. It's going to go faster. There's more force on it, right? No. Because what else does the acceleration depend on? Not just the force, but mass. What's the stupid physics definition of mass? Amount of inertia. Yeah, this has more force on it, but it's also harder to move. Because it has more inertia, it has more mass. This one only has 4 kilograms worth of inertia. This one has 8 kilograms worth of inertia. All right? What's the problem, John? You all right?
Yeah.
You mad there's no cake?
No.
So you get the same acceleration. You've got twice as much force, but you need twice as much force because you've got twice as much mass you're trying to move. And it results in the same acceleration. Good? So, a bunch of people said, I didn't understand number 15. Number 15 is about, instead of 2 bowling balls, it's about a feather and a bowling ball. So, that's a feather, the worst feather ever. That's a bowling ball. There's more force pulling the bowling ball down more. There's more force pulling the bowling ball down. Why doesn't it fall faster? Because it has more inertia, so it requires more force. Cool? Man, I am struggling with talking today. Are we good, you guys?
Yes.
All right. Problems on 13, 14, or 15? All right. 16. Yes? We need to do it, right?
What was the answer? Can you just give us the answer? Just the answer.
Nervous about not going over this. The answer to A is negative 9.8 meters a second squared. B is negative 8 meters per second squared. C is, yeah, sounds like we need to go over it. C is negative 5 meters a second squared. Yeah, and there's a bigger concept here. This one's about more than just getting the answers right. Okay? Because it's teaching you a concept which we have not learned about yet. Okay? All right, so air resistance. All right, so in every problem that we've done this year, we've ignored air resistance, and we will continue to ignore air resistance unless the problem like this specifically says something about air resistance, okay? So if it doesn't say anything about air resistance, assume it's a non-issue. If you see the words air resistance, then you got to think about air resistance, okay? All right, so here's the deal. Air resistance is a force, just like friction is a force, okay? When you walk down the hallway, you're pushing air out of the way. Okay? And the faster you walk, the more air you have to push. Okay? This is going to sound silly, but I want you guys to do this. Take your hand and move your hand slowly forward. It's nice, right? It's like a little like we're in one of those yoga commercials, right? Where they're advertising some medicine. Do you guys know what I'm talking about? Or no?
Yes.
Right. Okay, so when you do that, can you feel it? You're pushing the air. No. All right, so what I want you to do now is I want you to do it again, but this time go really fast. Right? And when you do that, you can feel the air. Look, you're pushing air with your hand. I can feel it. Do you feel it?
Yes.
Do it, Liz. You're not doing it. When you move your hand fast, you can feel it. You're pushing the air with your hand. All right? Can you feel it? I said, can you feel it? Thank you. All right, sorry, I suddenly turned into a gospel preacher there. All right. All right. to move per second, and so the more air resistance there is. All right, you knew this before you walked into the class, because if you're driving down the freeway and you stick your hand out the window, right? Whereas if you're walking down the hall, and, right, no big deal, right? So the faster you go, the more air resistance there is. Does that make sense? Okay, so with that in mind, let's go through number 16. So in number 16, Roy, who has a mass of 80 kilograms, is going to jump out of a helicopter. All right, what's his initial velocity? 0. Hold your hand at rest. Do you feel the air pushing it? No, because you're not moving the air at all, so there's no air resistance if you're not moving, right? So here's Roy in part A. He's got a mass of 80 kilograms, so the force of gravity is negative 784 newtons. Good? So, what's my net force here going to be, you guys? Negative 784, right? What's the acceleration going to be? Negative 9.8 meters a second squared, right? Now, as he falls, do you agree that he speeds up?
Yes.
Point for me. Which direction is he going to move? Down. So what's the air going to do to him? Push him up with some amount of air resistance. All right? So to do part B, here's the deal. Here's Roy. He's been falling for a few seconds. Gravity is still pulling him down with a force of negative 784 newtons. And in part B it says there's 144 newtons of air resistance. John, will you please spin around? I know you're not being super loud, but I don't know why it's distracting me. Thank you. Thank you. Okay. So as he moves down, air resistance is working against his downward motion by pushing him up. So is the net force still going to be 784? No. The net force now is negative 784 plus 184. It happens to give you negative 640 newtons. Good. So now we can find the acceleration. It's just net force over mass, right? So 640 over 80, because his mass is 80, if you forgot, is negative 8 meters a second squared. So I want you to notice two things about this acceleration that we got. First of all, if you ignore the sign, it's a smaller acceleration, right? So his speed is changing more gradually now than it was before. But it's still negative. So he's still gaining downward speed, just more gradually than he was before. Follow? So like originally he was gaining speed really quickly, right? Negative 9.8. Now he's still gaining speed, but only at negative 8. Right? So a slightly slower rate, but still gaining downward speed. And as he gains speed downward, what happens? More air resistance. Right? So a few seconds later, he'll have sped up, and now my air resistance is going to be bigger than 144. Right? Because he's still going faster as he moves down. Follow? So by the time you get to part C, here's Roy. He's now moving down even faster than he was before. That's him screaming. He was supposed to be smiling, but it didn't really turn out. All right, so gravity's pulling him down with 784 newtons. And C says now he's moving even faster. So now the air resistance is 384. What's his net force now, you guys? Negative 400 newtons, right? So the acceleration is net force over mass. 400 over 80 gives you negative 5 meters a second squared. So same observation as before. He's still gaining speed downwards, because it's still negative, but at a more gradual rate than he was before. But he's still gaining downward speed. And as he gains speed downward, what happens? You get more and more air resistance. So by the time you get to part D, here he is. Gravity's still pulling him down with that same force of 784. But now he's going even faster, and so the air resistance is even bigger. In this one, it's 720 newtons. So now the net force turns out to be negative 64 newtons. Okay? So these numbers that I chose for air resistance are somewhat arbitrary, but the point is they're getting bigger. Okay? So my net force now is negative 64 newtons, so the acceleration turns out to be negative 0.8 meters a second squared. So, still negative, so he's still going to gain downward speed, but very, very slowly now, right? Because that acceleration is almost zero. But, since he's going faster, what's going to happen? More air resistance, right? Eventually, as the air resistance gets bigger, the net force gets smaller, right? Numerically, that air resistance force is getting closer and closer to some other important number. No, it's not. It's getting farther from zero. The air resistance is getting bigger.
784.
The air resistance is getting closer to 784, isn't it? It's getting bigger and bigger and bigger and bigger. And eventually it's going to hit 784. That's part E. So let's think about what happens. Here's Roy. Gravity's pulling him down with negative 784 newtons. Eventually he's going to be going so fast that the air resistance will also be 784. That's an F. At that point, what's my net force, you guys? Zero. What's my acceleration? Zero. Does that mean he stops moving? It means he stops accelerating. So now his velocity is going to be constant. So the velocity at which this occurs, this is important. It says it on the sheets, but it's not in your notes anywhere. The velocity at which this occurs is called terminal velocity. All right, it's the fastest velocity that this object can achieve due to gravity. Because the idea is gravity is trying to make him go faster and faster and faster, but air resistance, he's moving so fast now that air resistance is completely canceling out the effects of gravity. And so he falls at a constant velocity. That velocity is called terminal velocity. Let me pause for a minute and let people process that. Questions with it? Yeah.
I have a question that's like time related. Is there a water resistance?
Absolutely, absolutely. Yeah, and it happens much faster, okay? Because like walking through the air, you don't really notice it, right? But have you ever tried to walk in a swimming pool? It sucks, right? Because water is more dense, right? So it turns out that the air resistance depends on a few things. It depends on the shape of the object, like sort of if it's conical or like that's why sports cars are pointy, right? Okay, because they're more aerodynamic, right? So it depends on the shape of the object. It depends on the cross-sectional area and the density of the fluid that it's going through. So if you drop a bowling ball off the Empire State Building, it'll go really, really fast before it hits terminal velocity. If you drop a bowling ball off of a cruise ship, it'll sink through the water and it'll speed up for a while, but it hits its terminal velocity much quicker because the water is more dense. So that's a great question. Yes, sir?
What is terminal velocity?
What is it?
Yeah.
It's the velocity, so as he's falling, he's speeding up,
Right.
right? As he speeds up, the air resistance gets bigger and bigger. Eventually, there's a point where the air resistance exactly cancels out gravity. Good?
Mm-hmm.
The velocity at which that occurs is terminal velocity. Because at that, why is it called terminal velocity, you guys? It's when you stop accelerating. You've terminated your acceleration. Make sense? All right. This doesn't mean you've hit the ground. It just means you can't fall any faster than you're already falling. Good? Sean, and then Allison?
So then that does vary based on the mass of an object?
It depends on the mass of the object and the shape of the object. I mean, a simple example is if I take this piece of paper, this hits its terminal velocity very quickly. See that? It's just like basically falling at a constant velocity, right? But if I crumple it up, I haven't changed the mass, but I've changed the shape of it. Now it has to be moving faster before it reaches its terminal velocity because it's pushing less air because it's smaller. Make sense? A little bit?
Kind of. So like, gravity affects two objects of different weights the same, but terminal velocity will still be different based on forces of gravity, based on mass.
Correct. So suppose I had a lead. So I've got somewhere in this room I have a tennis ball. All right. So tennis ball, right? Pretend I had a lead ball that was the exact same size.
Mm-hmm.
Okay, so this weighs, for simplicity, this weighs 2 newtons.
Okay.
Lead ball weighs 50 newtons.
Right.
When I drop them, they're both pushing the same amount of air because they have the same surface area. But this one only needs to push enough air to create 2 newtons worth of air resistance, which is going to happen pretty quickly. This one needs to push 50 newtons worth of air because it's heavier. So this one, the lead one, is going to have a higher terminal velocity than the tennis ball.
So terminal velocity is based more on, like if you were on the moon, terminal velocity would be the same then?
There is no terminal velocity on the moon. Anybody know why?
So no air.
No atmosphere. No atmosphere.
Okay.
Okay? So if they built the Empire State Building on the moon and we dropped stuff off of it, it would just speed up all the way down to the ground.
Can we do that?
Sure, yeah.
Nice.
Have at it. I need to borrow some money, but, yeah. Do I think what?
Do you think the terminal velocity is like the, do you think that's where like the misconception about like heavier objects are?
100%. 100%. Yeah, that's a really astute observation. Yeah. I mean, a lot of times you think, oh, heavy stuff falls slowly, right? Oh, sorry, I said that wrong. Light stuff falls slowly. And that's because, in general, lighter things reach their terminal velocity more quickly, which is why the paper floats, right? And why the feather floats. Okay? Renee and then Allison. Allison, you were supposed to be 7 hours ago. I'm sorry. I'll get you. I'm sorry. Renee, what do you got?
We haven't learned how to calculate it.
No, and we won't. I just started doing it with my AP class, and they were like, we hate you, Mr. Hacker, because it's some crazy calculus. It uses differential equations, and it's bonkers. So the reason this is so hard, you guys, this is one of only 2 forces we're going to talk about this year where the force is not constant. All right, most of the problems we've done so far, you push something and the force is constant, right? And if the force is constant, the net force is constant, which means your acceleration is constant. But here, since my acceleration's always changing, all those equations we learned in chapter 1, we can't use any of them anymore. Okay? And so it makes it, you can't solve air resistance problems without calculus. Okay? Allison, I'm sorry. Thank you for being patient.
I was just clarifying, so when something hits its terminal velocity, it stays at that same velocity until it hits the ground?
Correct.
Okay.
Or until you pull a parachute. What does a parachute do? Catches more air and it increases your air resistance force. All right, real quick before I get questions. Somebody asked this last hour. I don't know if this is what one of the 3 questions is, but in the movies, when you watch somebody pull a parachute, what do?
They go up.
They go up.
That's what I was going to ask like 10 minutes ago.
No, they don't go up. In the movies, it looks like they're going up, but what's actually happening, so let's suppose terminal velocity is, I'm going to make up a random number, 80 miles an hour. Okay, which is probably not too far off for a human. Okay, so the person's falling at 80 miles an hour. They open up their parachute. Suddenly, this air resistance force gets way bigger, produces a net force upwards. So now you've got a thing moving down, net force upwards. What's it going to do? Slow down, right? Good? All right, so now we've got this dude. He's falling at 80 miles an hour. He pulls the parachute. He slows down. So his speed goes 80, 75, 70, It slows down, right? So why in the movies, there's a frame. Here's, what's his name? Keanu Reeves, a great point, right? He's falling. He pulls the, okay, sure, Tom Cruise in Mission Impossible, whatever. He pulls the parachute and whoosh, he goes shooting up out of the screen, right? Why?
The
Cameraman's still falling at 80 miles an hour. Because he hasn't pulled the parachute yet. Does that make sense? So when you pull the parachute, you don't go up. You just go down slower than you would have if you hadn't pulled the parachute. Okay? So John, Griffo, Emmy, Allie, and then we got to move on or we're going to run out of time. Yeah. These are great questions, though. This is cool stuff. What do you got?
AP Physics, you have to be an AP Calc.
Yeah, it's strongly recommended. I have one student who's not this year, and he's struggling. So, yeah.
The parachute's big enough, can you get it to go up instead of...
No, because what's going to happen is, so the parachute makes you slow down. As you slow down, what happens to your force of air resistance? It decreases, right? So eventually, it equalizes again, but just at a slower velocity than it was before. Okay, good question. Emmy, and then Allie? Oh my gosh, yeah, you don't need to ask. Yeah, just grab a pass and go. Allie?
I think you already said this, but where did you get the 784 from?
It's the dude's weight. So the 7.4 video, or sorry, the, what chapter are we in? 3.4? What am I doing? So the dude in the problem has a mass of 80 kilograms. It told you that. So just times negative 9.8. Thank you for asking. I'm sorry if I glossed over that too quickly. Yeah, you don't understand that. And then everything else is out the window. No pun intended. Allie, you good?
Yeah.
Everybody good? Anybody ungood? Okay, cool. So, if you have a problem like this on a test or something, it'll be just like this. Either I'll give you the air resistance and the mass and you'll have to find the acceleration. You should understand that as you fall, the air resistance gets bigger, your acceleration and net force get less. You should understand that terminal velocity occurs when the air resistance cancels the gravity. Cool?
Cool.
All right, so it's not in the notes, but I think that problem covers that whole concept pretty thoroughly. All right, questions? Okay, so target checks. You guys took a target check on Friday. Let me pass those out. I think by the time I'm done passing them out, I'm not going to have time to go over them at all. Well, you know, I can say a couple quick things about them. All right, so let me pass out the target checks. Tower. All right. Julia.